No, sorry, I was wrong again. Okay, let's go into the detail. How do you actually create variable bathymetry? And so this, for example, is how a diffusion equation looks. Let's get the mouse on here. This is the diffusion equation. Sec derivative, both directions included, some diffusion coefficient. Okay? And then you just work out the finite difference equation. Have a look at the goes back to Taylor expansion series, and this again based on the Arakawa. So you have this is part of the iteration loop. You have a total water depth here, and then you have a correction, the diffusive correction, and you go through. And you can also specify coastline. So you can just set individual parts to zero. Zero gradient means zero gradient, and set individual. Okay, let's get started with the test. Here's the test. Southerly wind of 0.2 Pascal. Higher model domain, and I told you before that it gradually increased to this level. Everywhere the same wind. Maximum water depth is. Okay, let's have a look. Eventually, how this looks. Okay, this is what you actually get at the end is a steady state flow field. What does steady state mean? Steady state mean is no more changes. You get currents in the flow that remain the same all the time. And these are shown here. The wind goes from south to north, okay? And you get these flows. And this is one option in Scilab, that you can use colors to indicate the magnitude of the flow. I wouldn't know which color now means where you get the strongest flows. But however, you can see the structure. It doesn't change anymore, means after 10 days it will look the same, and after 15 days, and so on. Okay? So this is the structure of the flow that you get. And surprisingly, you actually get regions where the flow is opposite to the wind direction. You get return flow. Okay, why do you get return flow? So first of all, water is not compressible. So if you move water from south to north, it will pile up on the opposite side of the lake. And what it does, it will actually create a pressure gradient force. Okay? And the pressure gradient force will actually try to move water back from north to south. And this is essentially how you get these return flows. In this model, the flows can only be horizontal. This is one of the unrealistic aspects. You can't get any overturning, no vertical overturning. Yes, so you only get horizontal flows, and with that restraint, this is the circulation. Okay? And I actually have a simulation where you can see the initial adjustment towards this steady state. Look at it. This is how it starts. 2 days, 3 days. Now you can see it's already steady state. 5 days, and it would not change. No. So, all right. And that's the model test. That's interesting. It's a little bit boring because you get this steady state. But what you could imagine is what happens if you put an object afloat into this flow field. Okay, so for example, I put a float. If you can imagine, you put a float up here, and to the up northwest corner. But what happened is that the float would move with the current over to the other side, and then dependent on where you are, it might even go here to the north, or it might go to the west. All right, so that's what I want to do. I want to introduce you to Lagrangian floats. Floats that you place inside a current field, and that will move with a curve. And this gives you a little bit more interesting features of what you can do with the shallow water. All right.